Number 8 and 9. 8 might be a good one to pause the video and try this one. If you feel a bit apprehensive about that, then you're welcome to watch me do it. I'm going to set up my square root so I can start to place things. This is a perfect square because it is even. If I don't need to show any work, I can probably predict it's going to be n to the fourth. But if I need to, I can write it like this. And the rule in mod 5 was that if you're multiplying with the same base, you add the exponent. So that helps us justify that this is n to the eighth. And that's the best way to break this up. Notice I did not do n to the second times n to the sixth, which would work, but would probably just take more steps. Then we're going to go to t, and I'm going to make it t to the eighth times t to the first. So it is the highest exponent, basically one lower. And so that's going to be t to the fourth and t. So this is the perfect square part that's stuck inside. And then we've got 1728. So we just start picking. It is sort of guess and check, a little bit of luck, starting with a perfect square, maybe even starting with a large one, trying 49, trying 144, trying 36 goes into it 48 times. So that's a perfect square. And 48 is 6 times 8, but also 16 times 3 is handy. And that is a 4. And the 3 goes inside. And we clean up this kind of horrible looking answer into 24, n to the fourth, t to the fourth, root 3t. Number 9 with decimals, sort of like we saw in the 6-1a lesson. So this decimal, I can tell looks like it is based on 4, 4 being a perfect square. So maybe this is a 2 and a 2. Decimal place needs to be in the same spot so that these are pairs. And zero point 0.2 times 0.2 would be 0.04 with the decimal place moved 2 places to the left. Out comes only one of those. Nothing's left over of that. And now we've got a to the fourth times a. And that will be a squared and root a. All right. And then there was a set of instructions on the previous problems that said assume all variables represent positive real numbers. Let's think about why. It probably won't impact our answers currently in eighth grade, but in ninth grade, and it is important to understand why this is important. So let's pick an example, an easy one, and we're going to pick the square root of x squared. And the simplified version of that is x. These are inverse operations. So let's let x equal -3. And we'll plug this in using parentheses into this equation and see if it checks out. And we're not going to do anything fancy. We're just going to do PEMDAS. And so using parentheses here, -3 squared. So we're going to square our input value is going to be 9, and the square root will stay. In this one, I don't know why I wrote parentheses. I really didn't need it. And the square root of 9 is 3. And we have a -3, and this is false. So this is not checking out because in the original expression, the even exponent was killing the negative. And now that it has an odd exponent, that's not the case. And so it is common practice, although we don't need to do this. We don't need to do this in this lesson homework because it has this statement. But it is common practice that we use absolute value bars, which will also kill the negative and allow these to be equal. So, for example, square root of x to the sixth would technically be written as the absolute value of x cubed. But let's think about this. Is there maybe a case where we wouldn't need this? What about square root of x to the eighth? Oh, that's x to the fourth. So actually, we technically wouldn't need absolute value bars. So again, number 11. So now we're also going to start to introduce one of the other properties, which states that we can square root the numerator and denominator individually. And that allows us to take the square root of 4, which is 2, which is nice. And 75 has a 25 and a 3 in it. And out comes the 5, and the 3 is stuck inside. And we should also state that this answer is the same, that this answer is also the same. And we should also mention that in future lessons, we will be looking at the fact that the denominator must be rational. It cannot have a square root. And so if we had chosen to do this problem a different way and somehow we were left with a square root in the denominator, we would go back and think of a different way to tackle this problem. Luckily, this problem, the square root in the denominator fixed itself.